piece of hardware. Okay. Alright, what's it weighing?
15.45.
Alright, Marty.
Yeah, I'm out of your way.
About efficiency, right? The concept should be clear, everything should be rendered specific, and then we are in the game of maximizing output, minimizing input. So can you just summarize briefly how your project is more efficient? You guys are all disseminated in the crowd here. Just a few more bites of apple and then
we changed the pin connection to be more efficient, so it wasn't just the circular pin. And we moved the tension to the outside so there was more.
Yeah, and we changed to that top pin in order to load from the top instead of
okay, that might be your big step towards efficiency rather than difference, even though hopefully those other components do work better.
Well, the thing like loading at the top is now the 0 moment and then shift button to change the.
So you purify it as a truss system. All right, any money on where this is going to fail? That spin connection. Essentially, this is really a 4-inch arch, right? Except those are very close, so hopefully it's going to be stable. This could dislocate, right? You might see a problem with the cable. These are pretty beefy, pretty vertical. It's pretty faint. Okay. Could be a lateral stability issue. I don't know. I don't have I'm not putting my 401k on this, so as little as it's worth. All right. Well, everybody, Tyler, you got your eyewear on there?
Front row, no boxes.
Just want you to hang on to those peepers. So.
I really like
There you go, Pavel. I'm trusting that Luan and Andrew will understand the risks. All right, fire the Model T.
first settlement.
Wow. It wants to be straight. Yeah.
That was a really shallow lane.
How much?
1511.
1311.
1511.
1511.
That was scary.
Oh, do you have to hold it? Asymmetrical beams there. Clearly responding to the bending stress with an articulated flange top and bottom, right? Increase in depth where maximum moment occurs. You guys refined your wood system quite a lot. Great, okay. You guys all spread out. Anyhow, it looks tight, looks like a nice evolution. It should be lighter, more efficient. It's all going to come down to whether the connection between the web and the flanges can handle all the shear that we're going to see here. So looks good.
Here at the
Did we
bottom,
zero out?
bottom left here.
I think it had gotten up higher.
Is it 283?
283.
I think it was higher than, I mean, higher than before they checked it. I think it was higher than they checked it, so, before it started being.
In your lab notebooks, if you only put down the weight and the capacity of the project without a description of what's going on, you actually lose points. Not sure if you're serious or not, right? It's my way of encouraging you to write descriptions.
You guys are on deck.
Yeah. We're ready. We're ready.
7.78.
Is that with the Ventura in there?
Yes.
All right, just so I can show my wife.
You can. It's a keepsake.
No.
Wow.
Yeah, I don't know. What is it? I think they laminated.
I think it's going this way on the.
They laminated it like both ways.
The grain in the web is going east-west.
Yeah.
I guess it is.
Same contour, and then there was those marks there. Okay. Got a larger compression flange as opposed to a tensile flange. We should be looking for a shear problem right here, right? That's what we see in all the beams. Looks like you've got some tight lamination in there. You've got these dowels.
Oh,
right?
yeah.
Hopefully that'll help resist some of that shear. What is this wood? Looks like a white poplar, white piece of poplar. You guys select white, make sure you didn't get any green in there.
Yeah.
And what are the dowels made out of?
Huh?
What are the dowels made out of?
Some wood. What are the dowels?
All right, I just want to know whether they're going to work. Did you, is this sealed out? All right, any money on where this is going to fail?
Right, left, right.
All right, so we're pretty certain it's going to fail because of shear again?
Yeah. We tried to make it right.
See, all right, it looks tight. All right, fire away. Let me know if that's going to shoot out.
600. Nice.
Yeah.
Come on, left.
Little compression there. That's cool. There we go.
Something 14, something 15. When?
18, 15.
Yeah.
18, 15.
Oh wow.
Yeah, it's digital now, right?
26.41. 7,000?
All right, let's put the giant briefs in there. Is it a beam or is it a truss? I don't know. I think we're on the fence there now, right?
But didn't you say trusses had to have pin connections?
Well, I'm saying the ideal truss. I mean, we can still technically, well, in some sense, by patent, a Beardale truss is a Beardale truss.
Yeah.
A truss, and it doesn't have any triangulation, stress unique members, or pin connections. It's talking about the ideal, right?
Yeah.
That were afforded through triangulation and pin connections. So, through mathematical analysis, this was found to be the optimal depth. Beyond that, I guess we're just going deeper without as much of a return on the strength. So it's analyzed as a truss. You can see concentration of compression here, concentration of tension below. These pieces are larger to facilitate less stress, more force transfer from this piece to this piece, right? By doing that laterally, parallel grain, and a little bit of a plywood web in here. That should help with the shear and holding these cords or flanges apart at this point, right? Got a roller connection there, roller connection, right? Everybody get that one on the test? You look at the project, you think about all these other things, but it was just a dumb roller connection question. Did you see that? Yeah, you guys remember that one?
Talking about it like right now.
Showing them.
See what we do. Oh, settling in already.
Alright. Big pieces of wood here, folks.
4,000. 5,000.
Alright, I feel a little uncomfortable here.
Should we back everybody up?
Yeah.
Or we're done? I'm going to put the whiteboard in front of me.
Yeah, I think that's...
What is it up to right now?
See, I've gone through several hundreds of these before. There's a lot of force on there. They're big pieces of wood. I do actually have some concern right now. And this way, it'll just miss the limit.
It's gonna kill people.
We have a metal cage around here someplace. I don't remember where it is yet.
Censored.
You are my shield.
Everybody's going to move. All right.
So nervous. Who's yours?
Broke the. Broke the. What did it top out at? Yeah.
Stronger, but not. All right. I want to take a picture here before we.
5845. 5845. 5845. guys are on deck. You guys are on deck.
I just want to scoot over a little bit.
Okay, so we have an arch, right? But we wouldn't call it a 3-inch arch because we have supposedly a motor resisting connection here at the top. Roller. I've got some spreaders here to keep that around. If I were you guys, I would have brought that back just a little bit so it'd be more snug around the load applicator. That way you can save, you know, that times 4, so about 8 inches of tube. Because this is loaded on the outside, the arch is going to have a tendency to spread apart, right? Okay, so any money on where this is going to fail?
On the well.
Okay, I was going to say either the well or we're going to rip the sheet steel here and then it's going to lay down. All right.
Coming at you.
Wow.
What's it? 685?
Yep.
What's your guess?
My guess?
Yeah.
800 pounds on the cage.
This continuous compression cord with a pin connection leaves buckling. Right? Got significant grain continuity with a little bit of discontinuity just at that point. That's 1/2 inch, 5/8 inch deep. That's for the quarter.
We went for like 2,000 PSI, 3,000 PSI, like a second.
Yeah.
And it's not one, like, whenever it says main grade, it's never
Is it going to fail?
okay at all. It's like,
That's it. But not the well or the grade, right? Alright, just want to clarify.
I have no idea what this is.
I would have put my money on.
A little light attention.
Still freezing.
Freezing again?
It's already on.
Has to go right. Yeah, it should fit perfect. Okay.
So we've got a truss initially, right? We've got the cradle. The cradle provides autonomy from the top compression cord. These are biased to deform both upward and outward. It looks like they're biased more to deform upward, but also these systems that are put in place to constrain against that form bias, that control deformation, also look like they're biased to resist more upward than outward. So that stuff seems well calibrated. Have a little bit of a plate in here to help resist that outward deformation. Very attractive ferrule, right? Very well ordered. Hopefully it squeezes enough. Who's your ferruler?
He's got leverage.
Hopefully it's got penetration, but it's a very attractive ferrule. And I have never, ever said that was an attractive ferrule.
Congratulations. Kristen, what did it weigh?
9.05.
Nice track.
You have an attractive ferrule, yeah. You're an attractive ferruler.
Yeah. They lightened it up. And then with the all didn't theirs explode last night?
Oh, wow.
What do we got?
You get this guy.
Had it?
Oh, I got the same.
You got this to respond. That was my recommendation.
What did it go? How high did it go?
What's it away?
10.6.
You guys used to put that hole?
Yeah, it's crazy. Listen to it.
10.6.
Yep.
Okay, we can get the load applicator on there. Composite system. Got a wood compression flange. We've got steel web and tensile flange. Assuming this is going to help take care of the shear. Is that the intention? The shear is really going to occur between the tension and the compression. Right? But then hopefully this will be able to catch and slide over. You've got a bit of some space there where it's going to displace before that will catch. But I think the intention makes sense. Okay. Peekaboo for the shear, right? Everybody knows this is all about shear, right?
Zero shear.
Everybody get that question? Was everybody able to diagram the shear in the moment for our lab condition? That was the question that I told you I wouldn't tell you what it was. But I will remember your name.
Oh, good.
All right, let's go. See what happens when the bolt goes through, because there's that slack, the tension pulls and it shears the bottom of the bolt. That was, what, 1023. That's it maxed out.
Oh,
There's one, two. Come on, team, one, two.
What? Got that?
You put the load applicator on?
He's not taking pictures.
No, I just...
Hit the chassis though.
Thanks, Jimmy.
A lot of tension with the bias. Very nice laminated wood pieces here. And when that is going to deform outward, this is constrained with tension in here. And these little collars will slide forward and help prevent this from deforming outward.
Move to where they should hit it.
All right, fire it up.
Oh, they are sliding close too. Wow.
Off the well. Now it's just the wood.
We just have like really difficult nights putting it together.
Yeah. Wait, anyway, so.
You said it would move to the middle where it needs to be.
It's all that laminated wood.
Alright, the truss, discontinuous compression cord, two pin connections, tension around the bottom. Obviously a lot of tension going through here. I think you guys have good grain configuration relative to that. And look at that outstanding shear placement for the pin there. Everybody should appreciate that now, right? And with olive oil, I look, it's got an extra virgin kind of green quality to it. All right. It's not olive oil. It's a rub-on polyurethane. All right. And it's still standing.
Yeah, keep it with the
882. Yeah. Well, now you're just pressing the load application. Kaboom.
It's a little beat like that.
Wait, is he gonna take pictures?
No, you're fine. He will probably. Don't wait on my account, but I think he wants it.
Pictures first, or do you want us to?
Alright, if you want to put a load application on. Or 4-hinge darts. Technicality. Hollow wooden box beam. We want to maximize compression, but we still have some flexure to deal with. From a flexure standpoint, we can see that as the deepest part. Alright. Legal. Street legal, one of the few.
Now it's free to starch.
Dry chunks of resin that are on the M&M.
Yeah, next time you just need to have
Look at that.
Are they both labeled alike? Shut up. Same distance. Alright, you got some welds on the opposite side. You probably want to butter those up with a continuous piece. Alright. Same amount on that side. To the top, 4-inch arch, solid steel ball bearings there. Right. These little fittings that are going to hug into that. So this is very much a true kind of ball and socket thing. We have this system here for lateral stability. Roll, roll. Okay, this is biased outward, so. To be truly bold, you wouldn't even weld these pieces in there. Of course, we'd be here all day trying to get them set up in there. But, maybe just token welds to just facilitate that. But then to truly let this thing set would be nice. All right. Hopefully that'll close up soon, right?
That was too bold.
I didn't even get to take pictures.
Can it just set up again?
Okay. Can I say?
Oh, I broke the weld.
Well, that had to pull out. Well, it wouldn't have pulled out without something else failing, right? So the other weld failed. Yeah, they're all pulling out. A little aggressive with the grinder and grinder. So that weld.
All right.
Check out the grain orientation.
Yeah. All right. Let's put that on there, and I'll finish. Got a flint system working there, so we have a steel web buttoned up with some wood on the side. It's a very sophisticated, grain-conscious puzzle work on the inside there. Steel on the outside should correspond to the tension. Hopefully we'll see all of that stuff kind of tighten up to see that it's working. Regularly through bolted. So you go. Right? And so we don't want to have move laterally or all right. Sit away. 8.4. Oh yeah, I want to center focus.
I have to tell you that. No, I think it's like that.
Okay, so we've got a 3-hinge arch combined with this direct vector solution. In a way, you could have a 3-hinge arch here and a 3-hinge arch there, and then a 3-hinge arch put together. right? Then that would probably make it a 1, 2, 3, 4, 5-inch start, possibly. Okay, good grain alignment. Are these just glued this to this? Okay, so because we have the load applicator, the bearing surfaces that we do.
You smell what?
Pretty flat. I was going to say we could do some shear in your project there. Then if threaded rod, keep that from spreading. That is also just a glue connection, right? Where do you think it's going to fail?
What's the connection? Up top. Right there.
Glued.
Okay. What do you guys think?
Tension may have gone across.
Pin splitting the armor. Yeah.
Plastic. So what is it? No, it's not plastic. No.
Oh, that?
Yeah, it looks plastic. Like, that's why I think that's
Five. There you go.
Wow. You're fine.
Yeah, it's pretty in here. Nice.
Interesting.
The black backdrop, can't see that. No.
It just went all the way through the wood.
The weight of the one before that. The weight of the one. Weight to that.
Somewhere, right? Oh, can you? All right, then, yeah, if I can get a good shot. Yeah. Before you guys,
It's 9.6 pounds. 9.2 pounds.
Magnetic compressive melons here. So you're going naked up there, right? Everybody would expect that there'd be some tension there. So we're going to have a lot of tension in that piece right there. All right, you've got a lateral stability system on the inside. A little bit. Could be augmented. So are we going to see these babies break today? Alright, so we're going to watch the metal melt. We should get a line of tension there and a little bit firmer in the lateral stability part.
Possibility, I don't know.
Alright.
Yeah, no, that's the angle on those compressors. It's going to pop over the road.
Which way is it going?
Backwards.
diving move go?
Nothing broke. Not all.
Hey, I like your squats.
Look at the concept here. Obviously, we have an artist trying to take these two concentrated loads and distributing those more uniformly over these swap.
What's that one?
Okay, so we've got that amount of wood dedicated to that, and then these are all going to have arch action on one another. You've got an organizing spine, makes sense. Okay, I think it's a nice concept. I think, like you had mentioned, craft. You know, it will be very dependent upon that. Because in order for this to set, that has to close. So what we do hope is that at least everything like this is perfectly straight this way, because then it can settle out on that point and that point. But if it's not perfectly straight in this direction, some of the arch is going this way, and some of the arch is going that way. Or all of it's going this way, and all of it's going that way. That we'll see. The secondary things will happen in there, and that this piece is glued to another piece there, right?
Plug it in there.
Are these all monolithic pieces that have been carved out? You could see some shear. Let's see. It'll set up and shoot out, so shin guards. Now I say this and then, you know, Good deal. Thanks. Let's weigh in. 3.5. Oh yeah. One more. Yeah, we did. Cool. Well, we'll just.
Use a mold, and this is what we cut off of it. This is a two-part casting foam that we basically use to wrap carbon fiber and fiberglass around the actual body of it here. This part is hollow, but we actually built up material here for more specificity and just to take care of shear.
Okay. What about the order of the fabric?
Well, the mold comes actually up like this, so it gave us the opportunity to concentrate material here, and then it bends this way, so we concentrate material here.
And rather than wrapping it like we did the last time, we actually did strips on the length, and then wrapped it with one large piece.
So the order goes: there's a concentration of material here, and then a monolithic piece, and then more smaller pieces here, and then another monolithic piece, So it goes every other. And the final one is the whole thing vacuum.
What's the weight?
3.5 pounds.
What is it? 3.5 pounds. Here.
That's never going to come out of there.
Look, CSI on that video again.
570.
I'll show you.
Solid. 570.
570.
Throw the same PSI every time.
Who gets the broken third?
Tyler wants that one.
I still want to find a way to be in the picture.
You want the center because that's where the cup is.
I'm ready for the load applicator when you guys are.
Where the vacuum.
Everybody gets a piece.
Like on the final, what is this subject to?
Bending or buckling?
Compression, right? It's subject to compression, so it is not subject to flexure, right? Pin connection, axial load. This, on the other hand, is subject to flexure because we have a perpendicular load constraint to reactants right there. Okay, so again, giving you the answer to the file that you took. All right, what do you guys think this is going to fail? We're in there, right? We just imagine that because we've got to get from there to here, there is a little bit of moment that's going to take place right there. So I would bet that that little piece may break off. What do you guys think?
It's gonna survive.
Okay, that's it. Final project, 22209. I finished a lab ever. And so I look forward to working with you guys again.